A critically important topic in calculus is the idea of a continuous function, and it's related to limits. And what we mean by a continuous function is that a function is continuous at a point x equals a if the limit as x approaches a of f of x equals f of a. And so the implication there is threefold. One, we can say then that we know for sure that f of a exists. Then when you plug in a for x, you actually get a value. Secondly, we know then that the limit as x approaches a exists. So that means if you're coming from two different directions, you're going to approach the same value. And then lastly, directly from that definition, we see that the limit as x approaches a has to equal what the actual function value is. Alright, I'm going to draw a graph and show you where these rules can fail and what makes that discontinuous. Okay, we can see in this graph that we actually have three places where it's discontinuous. So at 1 here, at -1, we can see that if I plug in negative 1 into this function, f of x, f of -1, well, there's no colored in circle here. F of -1 is not defined. Therefore, it breaks our first statement, and it's discontinuous at -1. Okay, at +1, if I plug in f of 1, I'm actually at this value here. So f of 1 is defined, it does exist, however the limit does not, because as I approach 1 from this direction, I'm up here. As I approach 1 from this direction, I'm down here. Since those two places don't match, it's discontinuous there. And we call this a jump discontinuity. Okay, lastly, here the function value does exist at 2. If I plug in f of 2, or I plug in 2 into f, I get that value. Also, the limit exists, because as I come from that direction, I go up here, and as I come from 2 from the right, I'm up here, and so they approach the same value. However, the third rule is broken now, because the limit does not equal the function value. We can also discuss continuity on an interval. And so what we mean by continuous on an interval is just that the function is continuous at every single point in an interval. So in particular, we can say something like this. There are types of functions that are continuous everywhere on their domains. And these are some very common functions. So for example, polynomials are continuous on their domain. And it happens to be that for a polynomial, that's always going to be negative infinity to positive infinity. Rational functions are also continuous on their domain, and that would be anywhere that the denominator does not equal 0. So for the example we have here, where we have x minus 1 over x squared minus 1, all I have to worry about is the x squared minus 1 not being 0. So I solve this equation, which factors here, and so I know the things that make the denominator 0 or plus or minus 1. So those are the two places where this function is not continuous. So you would say it's continuous on negative infinity to -1, -1 to 1, and 1 to infinity. Alright, trigonometric functions are another example of functions that are continuous everywhere in their domain. Now the domains of trig functions vary depending on which function you're talking about. But the two common ones, sine and cosine, are both continuous everywhere. The others can be a little tricky, but if you just look those up, you should be fine. And lastly, we have root, or sometimes called radical functions. And again, those are continuous everywhere in their domain. And there's two different cases to worry about here. So here in my example, I have the square root of x plus 1. What you can't have, what's not in the domain here, is that we can't have negative square roots. So I need to solve this equation. X plus 1 is greater than or equal to 0, which means that x is greater than or equal to -1. So as an interval, you write that as -1 to infinity. The smallest you can have is -1, and it goes on from there. Now for a fifth root, or odd roots in general, I don't really care if I have a negative under the square root. For example, the cube root of negative 8 does exist. Negative 2 times negative 2 times negative 2 gives me negative 8. So for odd roots, your interval is always going to be negative infinity to positive infinity. For even roots, like squared root, fourth root, etc., you have to go back to this inequality. Alright, now that's not all we can say. We can also say that if you have f and g are continuous functions at x equals a, then so are these other functions. F plus g, f minus g, f times g, f divided by g, as long as g of a is not 0, right? You can't have a 0 in the denominator. Or c times f, where c is a constant. Okay, so here, continuity then is becoming a little bit more familiar to us, and so we can address questions like this. The question asks, where is g of x, which is x minus 1 over the square root of x plus 2, continuous? Okay, so what I can do here is think about g of x as being two things. It can be f of x over h of x, where f of x is this polynomial x minus 1, and h of x is the square root of x plus 2. Okay, so we just said that if you have two continuous functions, or if two functions are continuous at a certain point, when you divide them, they're still continuous at that point. So that will work here. And for the polynomial, we don't really have any concerns. That guy is continuous everywhere. H of x does have some concern though. It's a root function. So what I need to know is where is x plus 2 greater than or equal to 0? So that gives me x is greater than or equal to negative 2. So the temptation then would be to say that g of x is continuous on hard bracket negative 2 to infinity. And I'm claiming that's not quite correct, because if you remember when we said here, when you divide f divided by g, we need to make sure that g of a is not equal to 0. So here at negative 2, I have a 0 in the denominator. Okay, so this is actually not correct. The correct answer then would be soft bracket or parenthesis negative 2 to infinity. And so the only difference is here, the difference between these two is that the negative 2 is not included. But everywhere else, g of x is continuous. So why is this useful? Because now if I want to know, for example, the limit as x approaches 1 of x minus 1 over the square root of x plus 2, well, I know that this function, which was my g of x, I know that function is continuous negative 2 to infinity. So since 1 is in that range, all I have to do is plug it in. So I get 1 minus 1 over the square root of 1 plus 2, and so that actually equals 0. So the limit is x minus 1 over square root of x plus 2 equals 0. And that shows the power of continuous functions. I hope this idea makes sense. If you have any questions, please let me know. I'll be glad to help. Understanding continuous functions is a great thing to know in calculus, and it allows a lot of things to get easier for us if we know we're dealing with a continuous function. All right, if you have any questions, let me know. Thanks for watching.